In Module 1, we introduced the idea of orbitals and where we can find our electrons. Now, in the second principal energy level, so I'm on the second row of the periodic table, specifically talking about carbon, nitrogen, and oxygen. We have in the second principal energy level, so if we think of this as rungs of the ladder, this is the second rung of the ladder. We have an s orbital and we have 3 different p orbitals. Now the 1 and the 3, when I say we have 1 s and we have 3 p, are not referring to the principal energy level, but the number of orbitals that we have. So this is the second principal energy level, but we have 1 s orbital and 3 p orbitals. Now we come in when we are talking about our valence electrons. We tend to draw them like this. So if I'm looking at, say, carbon, carbon's valence shell has 2 electrons in the s and 1 electron each in 2 different p orbitals. When we go to covalently bond these electrons, remember all electrons are negatively charged and they want to get away from each other. The energy difference here between this s orbital and these p orbitals is relatively small. So in order to maximize the distance between these electrons, what happens is one of these electrons will get promoted. And when it does that, it equilibrates all of the energy of the orbitals into sp3 orbitals. So it ends up being an energy that's kind of between the s and the p. So now we have sp3 hybridized orbitals, and those electrons can spread out so that their negative charges aren't bumping into one another. They will pair up if they have to, if they're going to share, but initially they want to get away from each other. So this is a situation where carbon will make 4 different sigma bonds. A sigma bond is a single bond. So 4 different sigma bonds. So if I bring hydrogens in here, let's change my color. So if I bring a hydrogen in here, then each of these hydrogens can then fill these sp3 hybridized orbitals in order to make methane. So if I do it this way, then what I'm showing is that carbon is bonded to 4 different hydrogens here. This hydrogen is coming out towards us. This hydrogen is receding behind us. So this is how carbon will hybridize and make these 4 bonds. Now, if carbon is going to make a double bond, let's say carbon is going to, what should we draw? Maybe carbon dioxide. So this is carbon dioxide, and again, I'm going to be looking at carbon. Carbon comes in with its 4 valence electrons, but this time we have 2 pi bonds. These pi bonds are shown with the overlap of p orbitals. They are p orbitals only. So rather than having an s and 3 p orbitals to hybridize, what we end up with is then 2 of my p orbitals are occupied. So these are the pi bonds. These are both p orbitals. That leaves me an s orbital and 1 p orbital left in order to make sigma bonds. So these sigma bonds are made with hybridized orbitals, and it's basically whatever's left over. So there are 2 pi bonds, that means 2 p orbitals are occupied, so what's left over hybridizes. Now if we have a more complex situation, something like this. This is the molecule acetone. You aren't expected to know that yet. But here, this carbon atom has 1 pi bond showing. Remember, we come in with an s and 3 p's, but we have 1 pi bond showing. So we're going to occupy that p as a pi bond. What's left will hybridize in order to make our sigma bonds. So this is sp2. Similarly with oxygen. So if we have diatomic oxygen looks like this. Now we have lone pairs and a pi bond, but we're really only concerned with this pi bond. So oxygen comes in with an S and 3 P's. 1 P is occupied as a pi bond, so the rest will hybridize in order to get as far away from each other as possible. This is Sp2 hybridization. Now specifically, Sp2 hybridization will have trigonal planar geometry, electron geometry. And that's because what happens is that pi bond locks whatever's up here, it locks it into place. And then these two electron domains get away from it as much as possible. So it locks into a trigonal planar structure. And that's for all Sp2 hybridized atoms. Now, if we get to something like cyanide, here we have 2 pi bonds showing, 1 and 2. Let's see if I can highlight those just to make them clear. So here's a pi bond and here's a pi bond. That means I have 1 sigma, but I also have 1 lone pair. So what does that mean? Well, 2 pi bonds showing tells me that my S, P, 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 2 P's are occupied. That means I am Sp hybridized for this lone pair and this sigma bond. Now that an Sp hybridized atom is locked into a linear configuration. In order to have those P's overlap, the hybridized orbitals must be linear.